So good afternoon, everybody. So my name is Mohammed Mustafa. Today, me and my colleagues Firas, Ahmed, Saif, Basil, and Chris will be giving our final presentation on our project, which is sign language translator using hand pose estimation and LSTM. Okay, so through our presentation, first we will discuss our motivation and objective, and then we will explain our two pipelines, of course, providing some examples and demonstrations. And finally, we will talk about our contribution, limitations, and future work. Okay, so the main motivation behind our idea was the fact that people with speaking or hearing disabilities suffer a lot in their daily lives when they try to communicate with others. This actually makes them feel marginalized and not engaged in the society. And after we sat and we started thinking, we were able to reach 2 points. So the first one was that building an environment that would only help people with a disability to express their what they want to say or their to communicate with others wouldn't actually solve the problem completely, because there's the other side which will suffer a lot in understanding the signs. And the second point was that the other side, which are people who don't have such disability, play a very important component in the process of solving this issue. So we reached a conclusion to create an environment that would facilitate two-way communication and that would help in bridging the gap between people with such disability and others. And for us to reach or to solve our desired problem, we had to conduct research that would help us implement a high-performance model using our benchmark dataset that would compete with the state of the art.
So to give you a quick recap of our work of our architecture so far, what we'll be expecting is that we'll be having a signer that is standing in front of a camera, and then the camera will be detecting some key points of both hand palms of the signer through our media pipe module. Then the media pipe module will be passing some key points, the major key points of both palms to the LSTM-based model in order to detect the sequences of the sign done by the signer, which by then will be producing the top predictions to the user. More on that later, and I'll be talking about the dataset now. I will leave the floor to Chris.
Okay, so moving on to the dataset, we primarily had two datasets to choose from in our thesis project. First, we had the Microsoft ASL, and second, we had the WLASL, which stands for Word Level American Sign Language. And as you can see in the table on the very right, we have multiple variants of the Microsoft ASL. We have MS-ASL 200, MS-ASL 500, MS-ASL 1000, and finally we have our WLASL. Based on our analysis of all of these data sets, we found out that the ratio of the missing videos in the MS-ASL was much higher in it than it was in the WLASL. And that's why we based our decision to go for the WLASL as our data set. However, although the WLASL had a lower missing videos ratio in comparison to the Microsoft ASL, it yet had a low mean of videos per class or per word. As based on our analysis, we found that it had a mean of around 9.2 videos per word, which is not being even close to enough to move to the next step, which is the data pre-processing phase. And we mainly used the two approaches to tackle this problem. The first approach was to manually collect our data. And we basically were able to do this by manually going over different websites, different online public available data sets, publicly available databases, and integrating them into the publicly available data set of the WLASL. The second approach that we went for was to self-record ourselves using an HD video camera. However, we faced a major problem when we experimented with it in regards to the performance of the model. As we found out and we've concluded that the performance of the model had downgraded significantly when we've added these videos. And we've also found out that the main reason behind this was due to the fact that the key points were extracted at different positions, different setup, different orientations, and also at different translation magnitudes from the ones that were in the actual data set of the WLASL. And that's why eventually we chose to disregard these videos from our final data set. Eventually, we've been able to reach a mean of 22.69 videos per word before augmentation. And after augmentation, we've been able to successfully reach 121 videos per word average per word. And at this step, we're ready to go to the next step, which is the data pre-processing phase.
So second step in our implementation of the thirst pipeline was data pre-processing. This is a very essential step since this makes the data specifications for all the data across the videos to be the same. Our first stage in pre-processing was to have all videos the same number of frames. This number was 30 frames. And we need to make, in this step is so important because if we are taking 30 frames and we have a video of 70 frames, then there's a significant loss of data. And other way around, if we're taking, the video is 20 frames, then there's unnecessary additional data. So it's important to have the data consistent across all the videos. And the second step was to normalize the dimensions. And this step is very important since we need the positioning and the hand gestures to be consistent across most of the videos. So we have the dimensions across all videos within a specified range. And as my final step in our pre-processing was augmentation. And as my Chris, my colleague said, we faced a huge problem of lack of data. And so we had to resort to increasing the amount of data we had. At first, we used augmentation techniques that are adding noise to the videos, adding brightness. But since we are extracting key points that are coordinates in general, so this did not work and did not improve our results. And thus, we resorted to augmentation techniques that are rotations of small angles ranging from 10 to 30 degrees and from -10 to -30 degrees. And at this point, we're ready for the data to be provided to the model.
So as discussed earlier, the main components of our model based on what we have of our research based on two modules. The first one is the hand estimation module, and we resorted to using MediaPipe for that. The reason behind our decision is that MediaPipe offers multiple cross-platform implementations for Android or for cross-platform mobile applications or web. So our main aim was that in the future, our model would be integrated in systems. So that's why we used MediaPipe. So basically what we use from MediaPipe is the hand model, which basically collects around 21 key point from one palm of hand and in X, Y, and Z direction. So adding up to 63 key point per one palm. And then for both hands, we'll be having 126 key point per frame. So that we were having 30 frames and 126 key point per frame. And the final step is that we'll be passing the key points collected from the past module to our LSTM-based model. So basically, we choose LSTM because in sign language, a sign is composed of multiple movements that then denote to a word, and somehow some words can be closed in movements from one mode to another. So that's why we based our decision on LSTM-based models to detect the sequences in the movements and the key points we have been collecting. And then after passing through the LSTM part, it will be going through a fully connected layer in order to have strong and robust categorizations. And as you can note, we have dropouts in front of between the layers we're having in order to avoid overfitting. And this helped us significantly in the performance of our model during testing. Now we'll be talking about results.
Okay. So as you have been mentioning throughout the year, we are trying to reach two main goals. The first one is creating a benchmark data set, which will help the research community build upon it and test other models. And the second goal or aim is to provide a lightweight model that, as mentioned before, can work on multiple platforms. So in order to do so, we had to go through multiple various steps throughout the year. We had to compare our model to other models in 4 different stages. The first one being to comparing our initial results to publication results. However, this did not give us strong indication how our model was performing with respect to other models. So we had to move to another step, which is comparing our model to other researchers that implemented similar architectures or have similar approach, and try to reach the same goal at the end. Then for the third stage, we tested our model and other models on our data set, which was mentioned before during the presentation. However, we only tested on 2 levels, 20 words and 40 words. Then for the final and fourth step, we tested our model and the other models on our whole data set comprising of 100 words. However, we tested on 20, 40, 60, 80, and 100 words. And this will be explained why later during the presentation, why we divided testing into multiple stages. So when we were doing our research, we had to find papers that trying to solve the same problem, had similar approaches, and had promising results. So when we were doing our research, we concluded that there are 2 main researches that helped us to compare our results and our performance. One being from the Australian National University, which was actually the creator of the WALSL dataset, and another research from the University of Applied Sciences, which had a model comprising of 3 variants. For the first one, it used the I3 model, and for the second one, it used the media pipe and RNN model, comprising of 3 different variants, each one having different number of layers. Something to take into consideration before we move on to the results. The first thing that when we're doing our comparisons, we did not only run using the other model using our data set. However, we also followed the steps of every research. By that we mean, for example, if a certain paper or a certain model required some certain augmentation, running the model for a certain number of epochs, and so we had to follow their steps to have a better and robust comparison. And for the second note is that we tested only models or researchers that also tested their models on ESL, because we have found some other researchers that used that had very promising results. However, they used different sign languages, such as the Chinese Sign Language. However, the difference was that they have a very public, a large data set that helped them for training. And of course, the last thing is that we used our data set. Also, one point to take into consideration before moving on, the Australian National University, when they published their paper, they had different models tested when they're using their data set. However, you only opted for one to test upon or compare to, because the other models were unavailable to test upon. So moving on to the results, as you can see right here, we tested on the 20 and 40 words, and our model was the right side model. And as you can see right here, it had the highest performance, 96.8 and 94.6 respectively. 60 and 80 words, 94.23 and 92.5 respectively. And finally, for the 100 words test, we also had a high performance of 90.6%. To have a better sense of our results and how they compare to other models, this is a graph showing the trend of how each one of the 5 models performed when we increase the number of words by time. And even though all of them are decreasing in some way, however, as you can see, our model on the top, even though it's decreasing, however, the gradient it is decreasing by is very low compared to the other models. And this shows that our model is somewhat scalable if we increase the number of words in the future. Now we'll be showing some demos of our final model and how we test on real time using camera. On our left side, you will see us testing some words, and on the right side, you will see the founder of the American Sign Language University showing you the signs from the website. Another point is that, as you can see right here in the output, there are 5 outputs, not only one word on the left side right here. This is because we, during testing, we found that there are some words that had similar signs, such as if you saw right now, pizza and eat, they had very similar signs. So we wanted to give the user a better, if, for example, our model is further used for production, we wanted to give the user a better experience, so the user can choose the best word that he is trying to assign. And those words are listed based on their accuracy or their accuracy from the model. The first one on the left is our demo, and this is the founder of the American Sign Language University. This is our output. And this is the sign language expert showing the signs. On the left side here, our results in real time, and this is the sign language expert. Just have one single final demo, and we'll be moving on. Of course. I'm not sure if it's clear or not, but if you can see right here, the first one is mother. This is we had five results from the model, 5 predictions. From the left to the right side, you have the highest prediction. So the first thing detect, or the highest word predicted was mother. Continue. The second word is thank you. The third word is year. And finally is because. And this is the sign language expert.
So concerning our overview of architecture of our second pipeline, which is from audio to sign language, it first starts by receiving audio input from the users through a microphone, and this converted to text. Then we're using natural language processing to tokenize the sentences and get the origin of the word. And then each word is mapped to its corresponding sign before being visualized as an output on the screen. So the main part of this pipeline is natural language processing, and for this we use the natural language toolkit package because it has multiple techniques for natural language processing. So our first technique to get the origin of the word was called stemming, and it just reduces the word to its origin or stem in English language. And there's 2 types of stemmers, the Porter and Lancaster. Porter uses a simple technique called suffix stripping, which just removes the suffix from the end of the word, such as the ing or ed in the verb or the s in a noun. And the Lancaster stemmer is a much more iterative algorithm with rules of the 120 rules saved in an external table that are indexed by the last letter of the suffix. But these 2 approaches do not yield the words that are part of the English language at all times. Thus, we use the technique of limmatization, which also reduces the word to its origin or stem in the English languages, but ensures that it's linguistically correct. And finally, we use a tokenizer to divide the sentence into words so that each word is then mapped to a corresponding sign. And final step is to map the words to a specific sign. So if the word is present in our database, it's mapped to its corresponding video in a data set. If it's not a name of a city or a person, there's a corresponding video for it by our unified signer. And if it's not found, then it means it's a name of a city or a place or a country. Then it's fingerspelled using alphabets that are also present in our database using a unified signer. And here's a demo for our this second pipeline. These are all videos generated by our code. And here the sentence is Jack likes studying. Since Jack is a name of a person, then it's fingerspelled at the start. And then like and studying are videos from a dataset. Similarly, is the sentence is you finished work, and it's signed using videos that are also present in our dataset. Yes, exactly. Yes, these are all videos generated by the code we wrote.
So discussing what we have been our contribution throughout the year towards a research paper of what we have been developing. So first of all, we introduced a new benchmarking data set that is somehow scalable. that is based on the WLASL dataset, including some other public databases that were basically implemented in the very beginning for educational purposes and for research purposes, but were not merged together for a research to be done. And what we have been doing is that we have been merging these data to in a unified data set to be used later. Secondly, we succeeded in proposing a new sign-to-text deep learning model with a high performance, as the results have shown, compared with other models. In addition to being with high performance, it's of a lightweight. As you can see in the demo, it can predict in less than 1 second, which was the main goal from the very beginning, because as we said before, we wanted that model to be later on implemented in systems for community aid. Third, we proved that such model can work with cameras. As you can see in the demo, we can predict the top 5 predictions correctly, and in most of the times, the top prediction is the word that we are targeting. And finally, we explored the impact of various data augmentation techniques on data set with low mean of videos per classes. As Chris mentioned earlier, we had a 20 words per video mean, and after augmentation, we reached 120 mean, which helped us in training such powerful model.
Now for the limitations. First, there is the data set collection limitation. So we finished 100, we managed to train our machine model on 100 classes and to identify 100 classes. So in order to scale our model, in order to identify more classes, we need to add more data to our training in order to identify more classes. And this is our main obstacle for scaling our model. If we need to scale our model, we need to train the model on more data. So the next limitation is the camera detection. So as you have seen, we already use the camera in order to capture some frames with some resolution. So if it happens that the resolution is very low, where our key point detecting algorithm will fail to detect multiple points, which will then lower our model performance. So we need to solve such case. And moreover, the position and the angle of the signer relative to the camera will impact our model performance. Finally, for the word variations limitations, as you know, there are multiple variations of the same word that can happen in different contexts in the sentence. So we need to handle such cases. But in order to simplify in the model, we limited these variations into one variation for each word. So, however, this can be handled by increasing the number of classes and changing the name of the class and adding to the name its description. Finally, for our future work, so we have managed to create a model that works on 100 classes. So we're looking forward in order to implement this model on systems that will aid the community. And these systems can be like banks, hospitals, or supermarkets. Finally, we managed to create the model that identifies 100 classes. So we need to work to scale the model up and to identify the whole ASL language. So we'll collaborate with multiple researchers in order to create a huge data set that we could train the model on. And then finally, the references. These are the references. And thank you.